In this section of our text, we begin visiting something known as Hess's law, those relationships involving the heat of a reaction, delta H. When reactions are multiplied by a factor, the delta H of the reaction is multiplied by that same factor. Recall that delta H is extensive. That term simply says it depends upon quantities. How much you have will affect, as in what I just fixed in the last example, the amount of reactant and product will affect the size of delta H. The term extensive, mass is an extensive property. It changes with the amount of matter you contain. Let's suppose in this example, here's that combustion of diamond. Carbon as a solid combusts and produces carbon dioxide. Its heat energy that's released is negative 393.5 kJs. Suppose I double the amount. Doubling the moles will also then double the delta H. Twice the heat energy is then released. The same is true as if I tripled it. Whatever I did to distribute through coefficients, I do the same to the delta H. If I half it, I take half the delta H. If the reaction is exothermic in one direction, I flip the direction of the equation. The reaction is written in the reverse order. The sign also changes from negative to positive. If the reaction is reversed, the sign of delta H is opposite. Endothermic in one direction creates an exothermic in the opposite direction. These relationships involving delta H are known as Hess's law. Hess's law simply states the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. If the heat of reaction of step 3 is the sum of step 1 and step 2, the heat of reaction for step 1, when added to step 2, gives me the complete change of step number 3. The heat of reaction for an overall reaction is the sum of each individual step along the way. If chemical changes occur in a step-by-step fashion, we simply can add those steps together to find the overall equation. Let's model a Hess's law to see if that helps clarify. An example of Hess's law. Let's examine what we called elementary reactions. Elementary reaction 1, 2 units of NO combine with 1 unit of oxygen to form 2 units of NO2. An exothermic process, 116 kilojoules of heat released. Elementary reaction number 2 says 2 molecules of nitrogen react with 5 of oxygen and 2 of water to form 4 HNO3s, an exothermic value. And there's a third elementary reaction. Nitrogen and oxygen form 2 NOs. It's an endothermic process. What Hess's law is asking us to do is to combine these 3 equations so that when it's simplified, just as in algebra we can simplify things that are on the same or opposite side of the equal, we can do that as well with chemical equations. What we'd like to do is to be able to add these 3 equations so that when I simplify them, they give us the target. And that's what I refer to as this bottom one. This is our target equation. How do we build 3 units of NO2 plus 1 water, giving us 2 HNO3s and 1 molecule of NO? So I look at the first reactant in my target equation for no other reason than it's written first. And here's what I notice. I'm going to start going through my equations and see where it's written. I notice that NO2 is a product in the first equation. Is it written anywhere else, or is that the unique place? I don't see NO2 written any other place. So here's what I like about it. NO2, its unique position. So now that gives me some ideas of what we're going to need to do with this particular equation. It's on the wrong side of the arrow. It's supposed to be a reactant, but I see that it's a product. And instead of 2 units, we're supposed to have 3 units. Alrighty. what do I multiply 2 by to get to 3? 2x equals 3. So x, of course, is 3 halves, or 1.5. What I think I need to do is not only flip the direction, that I'm going to have to take 3 halves to distribute. And so when I do that, think about the delta H. You're going to flip the sign and multiply it by 3 halves. Let's pause and do that together. We're going to flip the direction. So 2 units of NO2. 2 times 2 is 6. 6 over 2 is 3. So 3 halves times 2 gives me the whole number of 3 units of NO2. Then the arrow. 3 halves times 1 is 3 halves oxygen. And 3 halves times 2 gives us 3 units of NO. The delta H for this equation, we flipped the signs because we flipped the direction. And let's just simply hit 3 halves of 116. And I get 174 kilojoules of heat. So what I've done so far is just examined the first reactant, NO2. The unique position in my building equations, these elementary reactions, was in the first target equation here. The NO2 is written as a product. It's on the wrong side of the arrow from my desired location, so I knew to flip the direction. I also had the wrong amount, so I took a fraction. 3 halves of 2 gives me the desired amount found in the target. So I flipped the direction and distributed a 3 half. When I flipped the direction, I flipped the sign on delta H, and I distributed 3 halves through the 116. Let's go on and examine the second reactant in our target equation. The second reactant is water. Let's begin skimming through our building equations to see where we locate water. I find it in the second equation, and it's the only place I find water. I like the side of the arrow it's on. It's on the left side as it is in the target, but I have twice the number that I need. So I'm going to leave the direction alone, but I'm going to distribute 1 half through that equation. I need half the number. So let's do that together. 1 half of 2 is 1 molecule of nitrogen, plus 1 half of 5, I'll just write as 5 halves oxygen, plus 1 half of 2 is a single water, 1 water. And we have an arrow. 1 half of 4 is 2 HNO3s. Let's adjust the delta H. Distributing 1 half. Now I'm going to leave the sign the same. It's still negative, but 256 cut in half is 128 kilojoules.